Hola guys, today we are going to start a new chapter, that is anti-infective agents. If you've not watched the earlier videos on basics of nomenclature and structures, I highly suggest you watch the video before starting this video to get a better sense of what we are going to learn here today. And if you have already watched the earlier video, let's get started. Today we will start with a new chapter, that is anti-infective agents. Under that, we will see the structures of local anti-infectives and the synthesis of some drugs. So under the classification of anti-infectives, other than local anti-infectives, we also have preservatives, antifungal agents, urinary tract anti-infectives, anti-tubercular agents, antiviral agents and anti-AIDS agents, anti-protozoal agents, anthelmintics, anti-scabies and anti-pedicular agents. For today, we will be only focusing on local anti-infectives. Okay, so next up we have antiseptics. What are antiseptics? Antiseptics are chemical compounds which are used to kill or inhibit the growth of microorganisms when applied to living tissues. Now, antiseptics can also be defined as agents which prevent sepsis by destroying or inhibiting growth of microorganisms on living tissue. Now, what are the ideal properties of antiseptics? It should have a rapid and lethal action against microorganisms. It should have low surface tension. Why do we need a low surface tension? This is to allow easy spreading on the wound. Then it should be non-irritating, non-allergic and low systemic toxicity. It should not lose its property in the presence of body fluid. Now this point is mostly because it has to be applied on the wound. The wound will have some body fluids. So in the presence of body fluids it should not lose its property. Now what are the uses? It can be used before a surgery or before injecting or administrating hypodermal injections. Next we have disinfectants. Now disinfectants are the chemical compounds that prevent transmission of infection or inhibit the growth of pathogenic microorganisms when applied to inanimate objects. The ideal properties are non-corrosive, rapid and lethal action against pathogens, aesthetically pleasing and non-staining. Now this has to be aesthetically pleasing because it has to be applied on inanimate objects. The uses are sterilization of surgical instruments, disinfection of rooms and bathrooms to kill microorganisms. Now you may ask, what is the difference between antiseptic and a disinfectant? So the major difference between antiseptic and disinfectant is antiseptic is applied to living tissue, whereas disinfectant is applied to inanimate objects. So antiseptic to living tissues and disinfectant to inanimate objects. Now an example of antiseptic can be Dettol. We will use Dettol on wounds. And disinfectant is any inanimate objects, like there is Lysol for floor cleaning. These are the two examples. Classification of anti-infectives. We have local anti-infectives. We have 8 different classes. So the first class would be alcohol or aldehyde related compounds. Second one, phenol and related compounds. Third, oxidizing agents. Then halogen-containing compounds. Next up we have cationic surfactants, dyes, nitrofuran derivatives, mercuric compounds. So what I will suggest is to learn the classifications better. First we will read the classification thoroughly, make it thorough and then go on to the structures. So the first one we have alcohol and aldehyde related compounds. In alcohol and related aldehyde related compounds we have ethyl alcohol, isopropyl alcohol, formaldehyde, ethylene oxide, glutaraldehyde. So in alcohol or aldehyde related problems we have 2 alcohols and 3 aldehyde related compounds. In alcohol we have ethyl alcohol and isopropyl alcohol. In aldehyde related compounds we have formaldehyde, ethylene oxide and glutaraldehyde. Next we will go on to phenol and related compounds. In phenol and related compounds we have phenol, parachlorophenol, hexachlorophene, cresol, paracresol, resorcinol, hexylresorcinol. So we will club phenol and para-chlorophenol together, hexachlorophene separately, cresol and para-cresol, resorcinol and para-resorcinol along with hexyl resorcinol. Now next we have oxidizing agents. In oxidizing agents we have hydrogen peroxide and hydrous benzoyl peroxide. So we will remember as oxidizing agents would be peroxides. Which two peroxide? Hydrogen peroxide and hydrous benzoyl peroxide. In halogen containing compounds we have povidone iodine and halozone. Next, in cationic surfactants we have benzalkonium chloride, cetyl pyridinium chloride. Now as we know cation is positively charged. So benzalkonium chloride, chloride with the negative. Cetyl pyridinium which is positively charged along with the chloride which is negatively charged. So cationic surfactants would be benzalkonium chloride, cetyl pyridinium chloride. In dyes we have gentian violet and methylene blue. In nitrofuran derivatives, we have nitrofurazone and furazolidine. In mercuric compounds, we have nitromersol and thiomersol. So, in nitrofuran derivatives, remember nitro and furan. Like any one or both of these can appear in the name. So, nitrofuran derivatives first is nitrofurazone and the other one is furazolidine. In mercuric compounds, we will have mersol or mersal as the common name. So we have two examples, that is nitromersol and thiomersal. Next, now let us get started with the alcohol and aldehyde related compounds. Let us see how to draw their structures. Now the first one being ethyl alcohol. Ethyl means two carbons. So two carbon with an alcohol group. So two carbons with an alcohol group, ethyl alcohol. Isopropyl alcohol. Isopropyl alcohol means the alcohol group, that is OH group, is attached to a carbon in the second position. As the second position, we have an OH attached to the second position of, what is this? Propane. So we will call it isopropyl alcohol. Next we have ethylene oxide. Ethylene oxide would be ethyl group CH2CH2. Since it is ethylene oxide, we will have a O attached to both these carbons. So we will get an ethylene oxide. Next we have a formaldehyde. Formaldehyde. Now this word form, if you check the common name, form means one carbon containing and we have aldehyde. So there is a carbon here, attached to it is the aldehyde group, that is double bond OH. C is directly attached to another H. Now glutaraldehyde. In glutaraldehyde we have 1, 2, 3, 4, 5. 5 carbon chain which is attached to two aldehyde groups. So a 5 carbon chain with two aldehyde groups at its end. This will be known as glutaraldehyde. For the synthesis of ethyl alcohol, we will start with ethene. That's CH2 double bond CH2. We will react this ethene with hydronium ion, that is H3O+. Now when we react hydronium ion with ethene, we will get, I will draw it this way, CH, H, H, C, which is attached to two hydrogens and a positive charge. The positive charge, since the valency of carbon is not satisfied. And along with this, since we used a single H here, we will also have a H2O, which is extra. So what we will do here is, when we add these two, we will get HCH, H connected to a C with an H and another H, and here we will connect with OH. So this will give you our ethyl alcohol. Next we have the synthesis of isopropyl alcohol. Now isopropyl alcohol, the synthesis is very easy. We will take a propene, that is 1, 2, 3. 3 carbon containing chain with a double bond. It will be named as propene. With propene we will take H2SO4 and water If we react H2SO4 and water in the presence of propene, we will get isopropyl alcohol. In the same mechanism which was shown last time, OH will attach over here. So we will get isopropyl alcohol. Next we have phenol and related compounds. In phenol and related compounds, first we have phenol, that is a benzene with a OH group. It will be named as phenol. Para-chlorophenol. So in the para position, according to this OH, para position there is a chlorine group. So para-chlorophenol. Cresol. Cresol is alternate to the hydroxyl group, that is the OH group. We have a methyl group, so we will call it cresol. Para-chlorocresol would be in the para position. According to this OH group, we will have a chlorine, so we will call it para-chlorocresol. Hexachlorophene would be in the position of, there would be 6 chloro groups in a phenol ring. Next we have resorcinol, that is OH at alternate positions. And last we have hexyl resorcinol, that is OH at alternative positions, and according to the para position of one of the hydroxyl groups, we will have a 6 carbon chain. So hexyl resorcinol. Now phenol, as we know, it is a benzene ring with the OH. Para-chloro is in the para position of the phenol. Cresol is OH and then methyl group in the para position. Now how do we remember this? Remember cresol. Cresol, it looks like CH3. So cresol, CRE, 3 letters, so CH3, and all means a phenol. So in a phenol group, in the meta position, there is a methyl group. Para-chlorocresol, cresol. So according to this, the para position. So para position of hydroxyl group, we have a chloro group. Next we have hexachlorophene. In hexachlorophene we have hexa. Hexa means 6. Chloro is chlorine group. Chloro is a chlorine group, and then phene. Then we have resorcinol. In resorcinol we have 2 hydroxyl groups. So resorcinol, we remember cresol resorcinol. Cresol is CH3. Then what is the other one remaining? We have OH. So an alternate OH group, it will stand for resorcinol. Hexyl resorcinol, hexyl means 6 and a resorcinol group. So resorcinol you draw first. Then according to the para position of the hydroxyl group, we will have a hexyl chain, that is a 6-membered chain. Next we have the synthesis of hexyl resorcinol. In hexyl resorcinol, first we will start with, let's see the root name, that is resorcinol. So we will start with, starting material would be resorcinol. So resorcinol will be a hydroxyl and an alternate hydroxyl. So this is our resorcinol. So first we will add a carbon chain to this one. To add a carbon chain to resorcinol, what we will do is we will use a hexanoic acid. Hexanoic acid will be written as CH3 and then 4 other carbons, and then 3 plus 2 would be 5, plus here C double bond O, OH. So this is our hexanoic acid. If we remove water from here, we will have OH will be removed from here, and then H will be removed from here. So we will have, to the resorcinol chain, we will attach a 6-membered chain. So we will attach CO, CH2 2 times, and then CH3. So this will be called hexanoyl resorcinol. Next we will let this compound undergo Clemmensen reaction. So what happens in Clemmensen reaction is, we have a ketone group converting to an alkane group. So for this, after doing Clemmensen reaction, we will get a ketone group converting to an alkane group. So OH, OH, and here this is a ketone group, that is, it was written like this. So we will have an H coming in place of this hydrogen. So we will have CH2, CH2 two times, and then CH3. So this is our hexyl resorcinol. For the synthesis of hexachlorophene, we will take two molecules of 1, 2, 4, 5 tetrachloro benzene. To this we will add NaOH in the presence of methanol at a very high temperature of 250 to 300 degrees Celsius. So what will happen over here is Na will go and form a bond with Cl, and OH will replace chlorine. So we will get two molecules of 1, 4, 5 trichloro phenol. Because of this, it will be named as phenol. Next we have, to this we will add formaldehyde in the presence of H2SO4, in the presence of concentrated H2SO4. So we will get these two molecules written side by side: chlorine, 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 OH. We'll write another molecule of the same one, OH, chlorine, 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 and since it's a formaldehyde, we will add here CH2 group. So we get hexachlorophene. Next we have the oxidizing agents. In oxidizing agents, I said we will have peroxides. Now we have hydrous benzoyl peroxide and a hydrogen peroxide. Now how do we remember this? Hydrous benzoyl peroxide and hydrogen peroxide. Now peroxide is when two oxygens are attached, okay, between two carbons, okay. So two oxygens attached by a covalent bond, and they should be between two other carbons. Now how do we draw a peroxide? Now there is a trick to drawing a peroxide, that is, first make a copy of the compound and then remove two hydrogens. For example, we have hydrogen peroxide. So lay them side by side, then you remove two hydrogens from between them and you attach them. We will draw for benzoyl peroxide. So instead of benzoyl peroxide, benzoyl is taken from benzoic acid. So let us draw benzoic acid. This is our benzoic acid, C double bond O, OH. Now let us draw another one. Let us make a copy. C double bond O and then OH. Now we will remove two hydrogens from between this. So we will get benzene with a C double bond O, then a O attached with another O, C double bond O attached with another benzene. So this will give us a hydrous benzoyl peroxide. Hydrogen peroxide, it will be H2O. So H, another H, then H, O, H. So we will remove these two hydrogens. We will get HOOH. Next up we have halogen-containing compounds. In halogen-containing compounds we have two examples, that is povidone iodine and halozone. Now what is povidone? Povidone, the full name for povidone is polyvinyl pyrrolidone. Polyvinyl pyrrolidone. Now what is a vinyl group? A vinyl group is as shown below here. It is a carbon attached to a benzene ring, among which the carbon and the next carbon we have a double bond. So this will be named as a vinyl group. Polyvinyl means multiple vinyl groups. Now what is a pyrrolidone? Now as you all have studied in the basic structure and nomenclature, we have seen that pyrrolidone is a mixture of pyrrole plus a one, that is a ketone. So how do we write a pyrrole? A pyrrole is a 5-membered ring with the nitrogen at the tip. Now since we need a ketone group, we will put a double bond O. So this is our pyrrolidone. So pyrrolidone attached with multiple vinyl groups. So we will here a carbon here attached with another carbon, and then it will go on for many times. Similarly here a carbon attached here, and then it will go on for n number of times. And since it is povidone iodine, we will have an iodine outside. Next we have a halazone. So in a halazone we will see a carboxylic acid on one side, and the para position to that we will have a carbonyl group. In this carbonyl group we will be substituting the hydrogens with two chlorides. So what is a carbonyl group? A carbonyl group is sulfur attached to two double bonds of oxygen, a single bond of nitrogen with two hydrogens. So here we will substitute these hydrogens with chlorine. So we will get a carbonyl group which is substituted with two chlorides and a carboxylic acid on the other side. With the benzene in the middle, we will call this as a halazone. Next we have the synthesis of halazone. Now how do we synthesize a halazone? As we had seen, the main basic structure was a benzene. So we take a benzene ring first. This benzene ring will undergo Friedel-Crafts alkylation. On Friedel-Crafts alkylation, in the presence of AlCl3, there will be a attachment of methyl group to the benzene ring. So we will call it toluene. To this toluene, we will add chlorosulfuric acid. So how do we write chlorosulfuric acid? Chlorosulfuric acid. Now it would be C double bond O and OH. Right, double bond O and OH. Now since it is a chlorosulfuric acid, we will add a sulfur group here. So this will be named chlorosulfuric acid. On the addition of chlorosulfuric acid, we will get in the toluene group, we will attach S double bond O and then Cl. This will be named as paratoluene sulfonyl chloride. What is removed here? Here we will remove this OH, and since there was a hydrogen attached over here, we will substitute this OH and this H and OH, it will form water, so there is removal of water over here. Then we will toluene sulfonyl chloride, we will add ammonia, that is NH3, and we will remove HCl. So we will this H and this chlorine will be removed. So we will get benzene with a CH3 with the S double bond O along with the NH2. This will be named P-toluene sulfonamide. To this we will add NaOCl, that is sodium hypochlorite, with the presence of excess of chlorine. So because of this we will get CH3 S double bond O attached with N and then Cl. Now next step is addition of oxygen, that is oxidation, in the presence of KMnO4, which is an oxidizing agent. So we will get, instead of the CH3, we will get C double bond OH. Along with this we will have S double bond O attached with. Okay, so next we will see cationic surfactants. In cationic surfactants, the first one which we have is benzalkonium chloride. Benzalkonium chloride will be a benzene with a quaternary nitrogen, that is a nitrogen attached with 4 R groups. So CH3, CH3, R group, a CH2, which is attached finally to a benzene. Now this R group can range from C8 to C12, C14, C16. So these are all the ranges R can take. So R can be 8, 12, 14, 16. Next we have cetyl pyridinium chloride. Cetyl pyridinium chloride. Cetyl pyridinium chloride. Cetyl would be 16. Pyridinium is 1 nitrogen in a benzene ring and chloride. So we have a pyridinium first to be drawn as a 6-membered double bonded ring with a nitrogen. Attached to this is a 16 carbon chain along with the, now since there are 1, 2, 3, 4 bonds here, we will give a positive charge to the nitrogen and Cl minus. So this will give you your cetyl pyridinium chloride. Next we have the synthesis of cetyl pyridinium chloride. For the synthesis of cetyl pyridinium chloride, we will take the starting material to be pyridinium, that is a 6-membered ring with a nitrogen and double bonds. So this will be called as pyridine. So in pyridine we will add cetyl chloride, that is cetyl chloride would be CH3, CH2 15 times. So this is a 16 carbon chain along with a chlorine. So this will be called cetyl chloride. So attachment of cetyl chloride would be this chlorine will be removed and this carbon will be attached to this nitrogen over here. So we will get attached to the pyridine ring, we will have the CH2 15 times and then a CH3. So we will get cetyl pyridinium chloride. Next we have the dyes. So in the dyes we have two examples. We have one is gentian violet and one is methylene blue. Now if you take a look at gentian violet, it looks very complicated but it's very easy. Trust me on this. It is a benzene ring attached with a nitrogen connected to 2 carbons. Now the same pattern is copied 3 times. Now you will say this lower carbon, this lower part is not the same, it is different. So what we do is, since it is attached to carbon and there are only three groups attached, if this is a single bond we'll have to give another hydrogen here. So what we do here is we will take a double bond attached to the carbon. Next we put a benzene ring. Now since there is a double bond here, we cannot put another double bond over here or over here, since this carbon will have 1, 2, 3, 4, 5 bonds. So what we do is we rearrange the double bonds and we make it alternate to this carbon, that is alternate to this carbon. So here we will put double bonds. Next here, since there is only one bond coming for nitrogen, we will have to maintain its valency, so we will give 2 bonds over here, a nitrogen attached to 2 methyl groups. And it's the same, since here there are 4 bonds attached to nitrogen, we will give it a positive charge and then a chloride will be attached to it. So this is your gentian violet. Now the same for methylene blue. This part is the same for both the sides. So it's a benzene ring attached with N and 2 methyl groups on both the sides, and in the middle it is attached with 1 nitrogen and 1 sulfur group. Now since this sulfur has 1, 2, 3 bonds, the valency of sulfur can be either 2 or 8. 2 or 6. So here it is 1, 2, 3, 1 extra. So we give a positive charge and a Cl minus. So here we have the same thing attached here. So what do we remember in dyes? A common trick is we have a benzene ring along with the nitrogen attached to 2 methyl groups. So in gentian violet it will be this one attached to a carbon and then the same with 2 other groups. In methylene blue it will be this group attached with the help of a nitrogen and a sulfur since it's a double bond here, here and here, here, so that it would be a positive charge and a Cl minus. Next we have the synthesis of gentian violet. Now let us just draw a small diagram of gentian violet in this corner so we know what we need. So we have a benzene ring, attached to it is a nitrogen with two methyl groups, then another carbon attached to the same ring once again, nitrogen with two methyl groups. Here will be a double bond followed by a benzene ring followed by double bond, nitrogen, two methyl groups, positive and chloride negative. Now this is the structure we are looking for. So to start this structure we will start with this part. So this part will be a starting material. So we will have a benzene with a nitrogen and two methyl groups. What will be this called? This will be called dimethyl. Now since a benzene with a NH2 is known as aniline, we will call this dimethyl aniline. We will take two molecules of dimethyl aniline and to this we will add carbonyl chloride. Carbonyl and then chloride. So since we will add this, there will be removal of two molecules of HCl. Now where we will take the two molecules of HCl from us is here, two hydrogens. So these hydrogens will be attached to these chlorines. So we will remove two molecules of HCl. So it will be benzene ring attached to N and then C double bond O attached to the other benzene ring along with the nitrogen and this. So after this we will add another molecule of the same dimethyl aniline to make up for this part over here. So we will add another dimethyl aniline. So a benzene ring with a nitrogen and two CH3CH3. So after addition of this, now if we want to add this ring to this part of the carbon, we already have a double bond O. So what we will do is we will shift this to the oxygen. So we will get a benzene ring with an N CH2CH3, then a carbon which is also attached to N CH3CH3. Down we need a carbon with a double bond attached to a benzene ring, then again a double bond, nitrogen, two benzene rings, since the valency is not maintained, a plus charge and a Cl minus. Now this has to be done in the presence of HCl so that you get the Cl minus. So that's all. Next we have nitrofuran derivatives. Now what is nitrofuran? Nitro and furan. So a nitro group attached to a furan ring, and then we have nitrofuran derivatives. So it would be a carbon attached to nitrogen and a R group. So nitrofuran and then a carbon attached to a nitrogen with double bond and then a R group. So nitrofurazone would be nitrofuran C attached to a nitrogen with double bonds and then a N group. So in this we have nitrofurazone, that is nitrofuran, and when we said C attached to nitrogen with double bonds and then any R group. So this R group over here is NH C double bond O NH2. Now this is a semi-carbazole derivative, that is semi-carbazole would be R N attached to another R, then another N attached to another R, C double bond O, N and R. This is a semi-carbazole. So if you look at this last thing very carefully, we will put this as NH, NH, C double bond O, NH, 2 here. Okay, this is also attached over here. So we will have NH2 C double bond O NH NH attached to this carbon. So this part will be a semi-carbazole. So we have nitrofurazone. Nitrofura and zone would be from the word semi-carbazole. Next we have a furazolidone. So what is a fura? Furazolidone. So we will have either nitro or fura in the name. So here we have fura. So since it's a nitrofuran derivative, we will have a nitro, then a furan, then we have a carbon which is attached to a nitrogen in double bonds, and then some R group. So since we have furazolidone, furazolidone, zolidone would be from the word oxazolidone. So oxazolidone is a nitrogen in a five-membered ring. We have oxazolidone. Oxa is oxygen, azo means nitrogen, and then O and E implicates a ketone. So we have nitrogen and oxygen at alternate positions, and in the middle we will have a double bond O, that is for ketone. So we will attach, instead of the R group, we will attach the oxazolidone, that is through the N, attachment through the N. So we have N, O, double bond O. So this is our furazolidone. Next we have the mercuric compounds. The two mercuric compounds are nitromersol and thiomersol. So nitromersol, so sol, mersol. So we have the common name of this structure is 3-hydroxy mercury 4-nitro orthocresol. So we will start naming from the CH3 group. So 1, 2, 3, 4. So first we have, in the third position we have hydroxy mercury. Now Hg is attached to O, so this will be called hydroxymercury. In the fourth position we have a nitro group, and then we have a orthocresol. Orthocresol as in it is OH is attached just besides, so in the ortho position according to cresol. So orthocresol. Next we have thiomersal. Thiomersal can be written as thio is sulfur, mersal is mercury. Okay. So what we will do is, it's a benzene ring. Attached to it is a sulfur. Next is mercury. Then CH3, CH3. Down we will have double bond O, O minus, and Na plus. This is a thiomersal. With that, we come to the end of the chapter anti-infectives, that is local anti-infectives. We'll be back with another video very soon. The next video would be on preservatives. So if you're interested in this series, please subscribe to our channel, like this video, and click on the bell icon to get notified for the next video. If you loved the video, please send a like and share it with your friends. Thank you. Mogasu.